correctly. And what we're gonna do is, what are we gonna do? We are going to basically we're still doing the Fourier transform stuff. So I want to kind of do a simple example. I want to try to do a simple example back and forth and see why and how that works. So Fourier transform. I mean, first of all, what's the difference between something like the Fourier transform in its pure form versus the Fourier transform, something like the algorithm like the FFT, fast Fourier transform, right? So that's kind of like another question that I have. I guess the algorithm is sort of this specific list of steps to do that given a specific function or something. The discrete Fourier transform, yeah. But I'm like mathematically, like in a more puristic way, like what, or how is this defined? No way, we don't want. I should change that. I should just change that. How can I change that so it always picks English by default? Maybe somewhere in the browser settings, I think. A finite sequence of equally spaced samples of a function into a same length sequence of equally spaced samples of a discrete time for a transform, which is a complex function frequency. I mean, that is a very specific algorithm. This I'm for sure. Fourier transform. Let's just stick to the Fourier transform. That's the integral, right? So definition, there are several common conventions for defining the Fourier transform of an integral function. One of them is these. The Fourier transform is denoted here by adding a circumflex. Yeah, that's it. When the independent variable represents time, t instead of x. This transform variable weird thing represents frequency. So that is a function of frequencies. I guess what this means is that with a given frequency, you have a specific function. I think that is what it means, right? Maybe I'm starting to understand this a bit better. So it's like, because you always have to think about the underlying. So what that kind of thing here means is that it's basically a map between, for all frequencies that are real, right? Because I think that's what it definitely means here. So say frequency 1, you map it to a specific function, right? We'll use the hat or something like that. Frequency 2, and then you have another function like 2 or 1, right? And so each of these, right, is, you can obtain that by doing the integral. So essentially what that means is it's basically a function that each input is a function. So it's a function that outputs functions, right? If I understand that correctly. Like let's do like, could we do a simple example where it's like the Fourier transform, like let's pick a function. Let's just actually take something that is basic, right? Although that might be difficult because it's a bit of an edge case, but let's pick something like, I don't know. Again, what was that app thing? Desmos? I think it's Desmos. Desmos graph calculator. So let's pick something like 3 times sine of x plus 2 times cosine of x times 3 or something like that, right? So let's pick up this function, right? So what will the Fourier transform give us in here, right? So basically what the Fourier transform will do here is, I mean, okay, so f of x, right? So f of x, because sometimes these concepts are so simple, it's more like trying to understand them at the meta level, and rather than just the technicalities of it. So the f of x is this like 3 sine of x plus 2 times cosine of 3x. That's f of x, right? And so, and now what I don't quite get is how do we approach like that, right? So what is this supposed to, like, how do I populate these shitty poo thing here? So this kind of weird e, like, is these something that you just say cool, so it depends on, that belongs to the reals, and then it just depends on how granular you want to go, like you want to, that's what I don't really get so much. So you go from f of x with the Fourier transform to this thing here, right? So that is known as the Fourier inversion theorem. That's the other thing. Angular frequency instead of ordinary frequency. There are other conventions. The Fourier transform on Euclidean space is treated differently, with the variable x of 100% position. So that is treated differently. Harmonic analysis. I will never know what the fuck these things are. Okay, so let's look at these. This is what we're interested in, probably. The Fourier transform can be defined in any arbitrary number of dimensions. As with the one-dimensional case, there are many conventions. For an integrable function fx, this article takes the definition so x and this thing here are n-dimensional vectors. And this is the dot product of the vectors. Alternatively, this can be viewed as belonging to the dual vector space, whatever that is, in which case the dot product becomes the contraction of x. All of the basic properties listed above hold for the n-dimensional Fourier transform, as do Plancherel's and Riemann theorem. If it's integral, the Fourier transform is still uniformly continuous, and the Riemann-Lebesgue lemma holds. Laplace transform, complex domain. Eigenfunctions. So we are here in, where are we here? Fourier transform. Why does this ultimately have this e component to it? This is what still confuses me. I mean, that is definitely the component that is used to kind of create that, the sort of the repeatable pattern, right? Because that's the point of a complex exponential. But why is it an integral? That's the Fourier series. Yeah, but that's these anyway. So there's no special case in here. Non-periodic functions. Sinusoids. See, I understand the concept of the Fourier series, but I don't understand the integral part of these. An example. Okay, so there's an actual example here. That's actually uncommon for the Wikipedia stuff. The following figures provide a visual illustration of how a frequency measures whether a frequency is present in a particular function. The depicted function oscillates at 3 Hz if t milliseconds and tends quickly to 0. The second factor in this equation is an envelope function that shapes the continuous sinusoid into short poles. Its general form is Gaussian function. This function was specially chosen to have a real Fourier transform that can be easily plotted. The first image contains its graph. In order to calculate, okay, so here there's like, in order to calculate like the Fourier transform of 3, it's like, how do we know that? How do we even, like, the second image shows the plot of the real and imaginary parts of this function. The real part of the integrand is almost always positive because when f is negative, the real part is negative as well. The result is that when you integrate the real part of the integrand, you get a relatively large number. On the other hand, when you try to measure a frequency that is not present, okay, so on the other hand, okay, I get it. So what this means is, so this is just a general recipe, right? So what this will ensure is that if you're trying to measure a frequency that is not present, then you're gonna get something like 0. On the other hand, when you try to measure a frequency that is not present, as in the case when we look at f5, you see that both real and imaginary components of this function vary rapidly between positive and negative values as plotted in the third image. Okay, so y 5 Hertz. Therefore, in this case, the integrand oscillates fast enough so that the integral is very small, and the value of the Fourier transform for that frequency is near 0. That's okay. So now I understand what this is telling us. So what this is telling us is this is just a formula that you can use to measure or kind of. That's why you have. Where was I? Here, right? So that's telling you, I get it. Okay, so that's actually building a function. That is why, okay, I get it. So that is why because I was always thinking, like, why is it that, like, how do you make the Fourier transform give you actually the frequencies, right? And then I would realize that in a lot of the examples you see online, you kind of see like, okay, so if your function is something like that, then what the Fourier transform does is kind of squish that into a function that it's telling you the frequencies, right? So it's like, it's a function that, for example, we're like this, right? And so we'll have peaks telling you kind of what is the combination of the different frequencies, and you have to interpret these values here as the frequencies that make up this function, right? That's why That's why you have that funky thing here. Because essentially what this is telling you is like, cool, so if the frequency is not going to be there, the integral will basically evaluate to 0, right? Cool. Now the interesting thing still to figure out, the thing that's still important to figure out is that why does this work like that, right? So you have the function, like, why does this tell you that? Why does this work? So you have a function and you multiply it by these, right? Like this, the exponential part is chosen like that for a very specific reason, which I don't know which one is it. But it's, I guess, what will... Well, let's analyze that, right? So let's try to, let's do it with our example. Let's do it with our example. So, but that's going to be, yeah, that's going to be impossible to plot. Well, let's simplify the example. Let's just, so the Fourier transform of the sinus function, so just something very simple, right? Wolfram alpha. Let's go. Awesome. Here you have, okay, yeah, that's the thing, the frequencies. Okay, now this starts to make more sense. So if the frequency, but I don't want W, the angular thing. I want, is there a way that I can, normalization, oscillation factor? Is there a way? I don't want that. I just want the, well, I mean, what's the frequency, right? The frequency is like, because that's just the amplitude. So the frequency in this case, it's just like pi something, right? Or is a factor of pi. Frequency of the sinus function. Oh, 1, okay. Okay, so one cycle occurs in 2 pi. Oh yeah, okay, so you're measuring it against 2 pi. That's here, right? So that's one cycle, that's a frequency. So what would happen in this case? How would we approach the, let's say f of x is just, yeah, yeah, that only changes like the amplitude, right? So that shouldn't have any effect. So let's just say that our example is just like that. And so now we'll basically, what will we do now? So we will, like how, okay, so you can carry that. So you probably carry that. So yeah, okay, so let's try to carry that. I don't know how, because how to do a complex integral. Fuck. I don't know. But let's forget about the integral for a second. So how does the f of x times this thing look like? So I have like 3 times sine x e to the power of minus 2 pi I x, and then this thing frequency here. Okay, that's interesting though, because this means that what will this function depend on? This pooing e is just something that it's part of the exponential. And I can't plot a complex exponential, can I? Yeah, well, I can. It's just going to be a fucking circle. Right? The question is how can we visualize that? So e to the power of like pi I is how do we integrate that? How do you fucking integrate that? You can't just integrate that. That's what's complicated, man. A complex exponential. But I guess the fact that it's complex is the trick here, right? Because you want things to cancel out probably whenever the frequency you choose is not the right one. But it seems to me that it's pretty, in a way, crazy that this factor here would have the impact, the only impact you need. But let's try to do the following. So okay, so we know that we can expand that, right, into I forget. So complex exponential Euler's identity. Euler's formula. There you go. So e and then factor. It's these. It's the complex sinus and real cosinus. So this means that in this case, right, this is basically so minus 2 pi x and that shit. And so e to the power of I and this thing is basically the cosine of all these of minus 2 pi x and that shit, plus I times the sinus of all that shit. Yeah, cool. Right, so this is the whole thing. And in this case, we're just multiplying the whole thing by sinus again, right? So it's like sinus times these and then sinus squared as the complex part. Sinus is the complex part. Sinus sine of x, which is kind of like cosine of minus 2 pi x and that thing here, right? So if this is 1, how does this look like? Because the real, so the complex part, so we can plot them separately, right? The complex part is I times sinus squared of, sine x times sine of minus 2 pi x and that shit here, right? So, God, how do I do that? And then this thing here, yeah. Guys, give me a second. I'm gonna take a quick call. Yeah, that was not the route. Anyway, so what do we do? So what if I multiply? Let's just get rid of this. I have sine times cosine of like, and we're just doing now for this little e crap thing being 1. we know that's somehow gonna be a peak in the outcome, in the sort of in the result function, right? And so the idea is minus 2 times pi. I like how the input works here. Times x. Let's zoom in here. So what is this doing? So this looks like that. And then the complex part looks like minus 2, no, minus what? That thing over here, right? So it's okay. So it's the same, just a little bit phased. Interesting. But it's just, what if you, I don't know, what if you just say times 5? What happens? Okay. Huh. So these integrals cancel or what? In the case of 1, in the case of 1, yeah, I mean, I don't know, when it comes to the integral, like, so the integral, like, how does this work? Like, it's minus cosine, right? Yeah, okay. So, but I don't even know what I'm thinking. What I'm thinking is, how do I evaluate the integrals in this case, right? What does add up and cancel out? Some of these things should cancel out, but I don't know exactly why. I guess it's got to do with these, maybe. Like, if the blue thing is the complex part, so you imagine it's like 90 degrees rotated or something. Do things cancel out? I don't know. So this part cancels out or what? Complex function. So it's a contour integration. Yeah, baby. I don't know. I don't want to go to Quora. I might do it in the. I really might have to get into that. Do I have to? So consider a complex value function ft of a real variable t. So ft is like something like that. Okay. So that's our case, which is, I assume, to be a piecewise continuous function defined in a closed interval. So the integral is the same, like just simply that. Okay. How is the complex integral with real variable of integration? So in this case, we would just integrate the two things. I guess the point is, if one of these integrals, I don't know, why would things cancel out? I just didn't know enough of that, so I might have to dive into that a bit more. But that's my intuition. Is something's got to cancel out here. If I just do times 5, then it's like times 5. They're getting even like the case of 2, right? It's just, I don't know, man. What was that saying? That was saying that basically, where was I? The example. No, that was not here. Here, not here. Here. The real is like that, and the imaginary is like that. Integrates to 0. So that's the original function. A real and imaginary parts of the transform 3 hertz. Okay, so you do actually, when you take that integral, you do actually count that as negative. Oh, sorry. Yeah, those are negative areas, of course, that, because the sine of x is not, it's just, no. What am I doing? That's also negative. I should just be, oh man. What is the integral? The integral should be negative here, right? Between 0 and what? And 2 pi? Yeah. I keep having those basic building blocks of this stuff, but simply it's just like I keep having blanks like that. Intuitively I thought that was the case, but then it confused me that the integral, yeah, because if I just make a general integral, it's like, yeah, sure, it's not going to be 0. It's just like in that frame is 0 to 2 pi, right? Because you cancel things, like the stuff that's above 0 is plus, the stuff that's below is 0, right? So the point here is, in this case, if you just have 1, like, okay, but what's the period? It's funny, like, how is that? Change. So that basically, this is what it's doing. It's just translating by multiplying a function by this thing here. Is it that you're able to, why 2 pi x, why? It's like a y these, y minus. If it would be plus, then what would happen? Nothing. God. But it's got to do with the behavior of this multiplication by something simple. Not something simple, something which is like, it's a pure wave thingy, right? So I'm trying to think about what's the intuition about this. It definitely behaves. So this is definitely one thing where you'd say, like, for example, take it doesn't have an easy thing. Like you can't. Yes, there's a pattern, right? So, but for some reason you're really here taking the 2 pi thing. Maybe because that's the example of when things vanish, right? And in this case, it's maybe different the way you interpret this, but it seems to make sense. So the real part here is it's positive, right? Whereas in this case, the imaginary part cancels. While here things for 5 hertz don't no, for 5 hertz things cancel, so they both get to 0. So that's why you have the Fourier transform here. Okay, so that's the result of the Fourier transform is that at these values you get the highest. And it's really crazy that I think that actually tells you the proportion. The value corresponds to the integrals. Yeah, this is the integrals exactly. I get the intuition. I definitely get the intuition, but I'm not so sure I can work out all the mechanics of these. And or maybe I get the technique, but I don't think I understand why it works. As in, like, why multiplying by this factor has this effect. And just forget about the complex part. We can just keep just the real part, right? Just stay with the real part, like. That's interesting. 3, 4, 5, 6, 7, 8, 9. Like, the higher the frequency, you know, the more you kind of get this pattern where things just obviously cancel out. And the one is not that obvious because these are 2 negatives. So one of these cancels out. Oh yeah, that's a bit dangerous, right? Because here you have like a minus 0.5, minus 0.6, and here you have like a minus 0.9. So, Fourier. Maybe that's just not that obvious. The Fourier transform of the sine and cosine functions. Like, maybe I'm just taking an example that I think it's simple and it's actually not simple. This is definitely not simple. So, whoa. Nah, it's not that simple. Look at that. That is definitely not that simple. I thought it would be something simple though. Why isn't it simple? I thought it would be just something simple. I'll leave it here, guys. I don't have any more time. But I thought it would be something simple. I just picked the wrong example, I think. Like what would the integral give me in this case, right? It's something complicated. I get the mechanism, but I don't really fully grasp why it works. Think about this a bit. I'll think about this a bit more. Bye bye.